because so much of the microelectronics industry and the industries that sit above that, automotive, telco, whatever, depend on just-in-time manufacturing principles. So at no point does anybody want to be sat on a huge pile of stock that they aren't able to shift. And so we have to work to those principles in order to do it. So eventually the way that I'd like to see it is basically we have Amazon warehouse-esque places globally where our satellites land and get delivered, and then it just goes out from there, and within 24 hours it's with the customer type thing, because that's the way that the business model works, because that's the way manufacturing already works. Nobody who currently manufactures a product here on Earth will change the way they operate to include something from space. You have to take the thing that comes from space and make it fit the way in which we currently do things to have it adopted.
Welcome to the Lab to Market Leadership Podcast. Too many advanced science and engineering companies fail to deliver their innovations from the lab to the market. We are on a mission to change that. My name is Chris Reichhelm, and I'm the founder and CEO of Deep Tech Leaders. Each week, we speak with some of the world's leading entrepreneurs, investors, corporates, and policymakers about what it takes to succeed on the lab to market journey. Join us. We're talking today about ridiculously audacious goals and the value created in pursuit of those goals. And to illustrate this, I want to go back in time and up in space. In 1961, President Kennedy announces to the world that America will land a man on the moon and return him home safely by the end of the decade. 8 years later, this happens. And to prove it's not a one-off, NASA and their Apollo program, they repeat this exercise multiple times over the course of the next 3 years. It was and remains for many the greatest technological feat in humanity's history. But beyond demonstrating to the world that America had won the space race, what was the value created in this exercise? Was it all geopolitics? Or was there something else? To my mind, perhaps not surprisingly, the value created by so-called winning or being perceived to win the space race was dwarfed by comparison with the value that emerged from innovations that were either defined or accelerated because of the Apollo program. And in fact, I would go further. I would say that the world of technology and science that we inhabit today was in part birthed by the Apollo program. Innovations like microchips, not defined, but accelerated thanks to the Apollo program. Innovations in software, particularly validation and testing, project management. Innovations like telemetry, like remote health monitoring systems, like advanced materials, novel alloys, composites, like complex medical imaging technologies, like solar energy technologies, battery technologies, water purification systems, freeze-dried food. All of these were, again, not just defined, or in some cases not defined at all, but they were accelerated in pursuit of this ridiculously audacious goal. Deep tech companies, deep tech ventures are moonshot in their very nature. They're reaching for very audacious goals. And there is a tremendous amount of value, hopefully, in realization of those goals, in realizing artificial general intelligence, in realizing things like fault-tolerant quantum computing, to be sure. But I would argue that there is also just as much value, potentially, in the pursuit of that goal, which is not the same as reaching the goal itself. To help me chew on this some more, I'm delighted to be joined by Josh Western, who is the co-founder and CEO of a company called SpaceForge. SpaceForge is one of the UK's leading space companies. And as you'd expect, they have a ridiculously audacious goal of making advanced materials in space, more particularly making advanced materials in microgravity conditions, and then returning those advanced materials by satellite. That also functions as a mini factory. I'm really interested in getting into this with Josh and in seeing in particular how he sees the journey of value creation within Space Forge. As ever, this is going to be a great conversation. I hope you enjoy. Let's get into it. Josh Western, thank you so much for joining me.
Chris, appreciate it. Really good to be here.
Manufacturing advanced materials in microgravity conditions, i.e. space, is amongst the more audacious propositions that I've come across in all my years in deep tech. What led you and your co-founder to believe that actually manufacturing these materials in space was the way forward?
In both cases, I think I'm probably starting with a history lesson. The advent of making things in space is not new. We have been successfully doing microgravity research and development around materials, both organic and inorganic, since the 1960s. At the same time, we've been returning things from space successfully as human civilization since the late 1950s. And in mine and Andy's own time as to why we do this, one, we had to do something that mattered. And second, we were really bored. We were two very small cogs in a very large machine. And there wasn't the passion. I mean, you're absolutely right to say that Space Forge is audacious. My view would probably be is pretty much as audacious as you can get. And every now and again, I do remind myself I could have started a much easier company. But then I probably would have been as many times as bored, as many times as that would have been easier as well. When it comes to what we do with the in-space manufacturing of semiconductors, that as a technology has existed since 1973. We are stood on the shoulders of giants when it comes to knowing this is possible. It's just that the semiconductor industry has reached a point of maturity for materials that aren't silicon, that the demand curve and the signal and the need globally for these materials have now arrived. So the one thing I can always say with certainty is that I might be too early, I might be at the right time, but I'm definitely not too late to be able to do this.
And so in setting Space Forge up, was this primarily led by the market? You know, the development of these materials, as I understand it, you're making substrates for semiconductors. Right. Was that a market-led thing? And that is recognizing that silicon, the life of silicon may be reaching its final destination? Or was it, how much was it a function of this is ridiculously audacious, we should do it, and if we don't get it right with, let's say, substrates for semiconductors, we'll find something else? And how much was it actually responding to that semiconductor and industrial need?
So it, at least for us, has always been about semiconductors. So when we started in a garage on the outskirts of the city, we started with a 3D printer, a vacuum pump, and some very crude electronics to attempt to make basically a reactor where you grow these semiconductor crystals. What we very quickly found out in the early stages of our journey were two things. One, any available in-space infrastructure that could actually host us to be able to do this was wildly expensive. Second, if we weren't to go and use something on the market, anybody we approached to help build it for us thought we were crazy, and so were unwilling to do it, which quite frankly is fair enough. But that's what led to a much larger creation around what Space Forge does, because we had to build our own architecture to facilitate this being possible. When we started back in 2018, nobody cared. about semiconductors, apart from the people who were in the industry. It's only through, kind of the onset of COVID, war in Ukraine, the release of chip war, but people have actually really begun to understand just how important these things are. Literally every sector globally in every country depends on them. And at the same time, how fragile the entire global supply chain that makes this entire industry up is, irrespective, even if you set aside the geopolitics of Taiwan and everything else, there is no one country that excels at every aspect of semiconductor production. There are nations, groups of nations, which lead in certain parts. Of course, Taiwan leads in the manufacturing of the wafers. The UK has an enormous opportunity around IP with, historically speaking, companies like ARM, but it also has really good industry around compounds. The US, of course, has an incredibly dominant microelectronics business with respect to the packaging and the design considerations when it comes to the products that you do that with, which have, of course, resulted in companies like NVIDIA and Apple. But that is all at a time whereby it's less that the road for silicon is ending. Silicon is a manufacturing marvel. You're literally taking the right type of sand, and it's enabling us right now to have this conversation. What is impressive about silicon is how much money goes into producing something so cheaply. So, latest fab or whatever is 20 billion, but it's trying to produce components that cost less than a penny. It's actually quite remarkable how much effort it takes to make silicon economics make sense. The challenge is that the demand for where silicon plays has now massively increased. So, for example, the people are loving to talk right now about artificial intelligence and data centers and its energy consumption and its potential water use and everything else. The real bottleneck is not the availability of that compute. The bottleneck is how much power it takes to drive that compute. If you can improve the outcome of the energy that goes into that data center that then drives the large language models or whatever it is that you're working with, then you are able to redress the balance between the energy consumption and the useful output. The challenge is energy consumes a lot of power in terms of getting it from the grid into something useful. That's where something like a compound helps. So what we do as SpaceForge is we underpin the infrastructure that effectively makes pretty much all of our lives easier.
And you underpin it how exactly? By creating a more efficient substrate?
Pretty much. So all semiconductors start as an inorganic crystal structure. So silicon is one material, it's silicon, but you also have compound semiconductors. Gallium nitride and silicon carbide are probably two of the most well adopted. Yep. You find silicon carbide in electric vehicles, you find gallium nitride in things like 5G towers. And by their very nature, they're different materials smushed together into a crystal form. The performance of that system, where that compound semiconductor substrate is eventually deployed in the form of a chip, starts its dependency on how good a crystal structure you have. If you can improve how pure or how good that crystal structure is, you can improve the end system outcome of wherever that chip gets deployed. So in many ways, what we do is the material science that enables us to have a purer chip that enables us to either have higher performance, consume less energy, worry less about heat, and so forth. We don't prescribe to our customers how they deploy our materials. We just offer them the opportunity to have a better outcome.
Yes. Understood. But for SpaceForge, the materials themselves are definitely not your only innovation. You're obviously creating these novel, far more efficient substrates, which can impact the entire value chain and the entire system in a what sounds like a fairly significant way. But you're also, as part of that, it sounds like you've got to create these mini manufacturing facilities that are from what I can understand, also satellites. You need them to be returnable too. And just from the bit of research that we've done, so you've got these reusable orbital microfactories, if you will, but then you've also got this return and recovery stack with what I understand the Predictive Deployable, which is the reusable heat shield, and you've got your predictive reentry and landing software, and a number of other innovations too. So it doesn't appear that the materials are the only bet you're making. It appears that you're also creating innovation in other areas that are related to delivering on your end goal. Is that fair?
Sort of. So what we're doing at SpaceForge has all been done before, irrespective of what technology piece you choose. Effectively, at no point in history have all of them been brought together, at least in a commercial sense. So we are certainly new in that form. The list you read out there betrays the fact that basically SpaceForge, if it so chose, could be about 5 different startups, and each one of them could be successful. But the real multiplier comes from when you have those technologies come together. And the challenge is that if you only did one aspect of it, is that the other 4 can't be as successful. So as an example, we are by no means the only reentry vehicle on the market. We are by no means the only in-space manufacturing company on the market. The challenge is that if you have only the vehicle or you have only the payload, is that very rarely do the opportunities actually align with respect to, does that vehicle that you're re-entering have a gentle enough re-entry to allow you to bring your product back safely? Does it have enough power for you to actually do your production process? Similarly, the vehicle has to say, well, perhaps that process takes too long and I need to be up and down in 2 weeks to make my business model work. So I can't sustain something that works, or needs to be up in space for 3 months, 6 months, or whatever it is. So it's only by having a view across the whole stack, which we were forced to have because nobody wanted to build it at the start, has allowed us to actually carve our own wedge when it comes to having a position within this market. What I would say is, despite the historical connotations that all of our various and respective technologies have, the key for us at the moment from SpaceForge is we are certainly unique from a European standpoint. And the way in which politics is caught up both in the space arena and in the semiconductor arena, to understand the importance and to understand the need to not be reliant on potential other partners or other nations for access to these things, whether or not that's your semiconductor supply chain, whether or not that's getting to and from space. We are seeing almost like a renaissance with respect to the considerations that are now given to these two streams from a European and from a British perspective in driving the need to have these as strategic industries that can actually be relied upon and then go on to underpin all of the industrial bases pretty much for all of the other technologies. You can't have an automotive industry today without having a semiconductor industry as an example.
Absolutely. There are a whole bunch of interesting things you just said there. I guess let me tack into the first one. All of these different domains, all of these different disciplines. I mean, that is an enormous, I suppose, is that kind of the verticalization of what you're doing. And you've seen this in other big deep tech organizations, if you want to call it Tesla, a big deep tech organization. They've verticalized. They don't rely on much of a supply chain. They try to do everything themselves. They've created their own production line and a lot of their own materials and obviously their own software and batteries and all of that kind of stuff. Although the battery technology comes from a variety of different sources. But it sounds like you're doing something similar. So you couldn't find the partners quite. So you've decided to do it yourself. What kind of, for a startup that is ultimately limited by resources, both in terms of capital and talent and so on, how do you manage that? Because each one of these things, as you said, there are probably about 5 different startups there. You're bundling them all together. I totally get why you would do that. How do you prioritize that? How is it addressing that challenge? How is it? That's that's one hell of a mouthful. How do you handle that?
We came up with an expression actually at the start of this year, which was prima payloadia. So payload first. That by the virtue of its
that's the priority. The payload.
Well, so by the virtue of its name itself, right? Payload. That's where the payday is. And there are a lot of space companies out there that basically forget that. And they just want to build the coolest satellite, not necessarily what is the part of that satellite that is actually generating the revenue, creating the profit. Genuinely, you can follow the cycle around, creating the employment that allows those jobs to exist in the first place. If you as a company can't support your payload, the rest of the architecture basically becomes invalid, because the payload is what drives the market that we exist and operate in as SpaceForge. There would be no point in having any re-entry vehicle on the market unless we have something that was actually worth bringing back. And so each time we went through this loop, we came back to this, and we're very fortunate at SpaceForge that, again, we timed the wave right with respect to both semiconductors and our focus on the technology and the heritage and the expertise around the team that we had already built. But when it comes to the resourcing aspect, as much as there are those different technologies, a huge amount of them rely on the same skill set. So I would say broadly, 50% of our company are material scientists, and the other 50% are spacecraft engineers. The difference between spacecraft engineering and other engineering are two things. One, it has to survive a much more challenging environment than most other things that you engineer. And second, the funny suit that you have to wear while you're building it. That's pretty much it. So you have the ability to bring engineers from all sorts of disciplines and all sorts of other verticals, aerospace, automotive, wherever, to work on a technology that they believe in. All of that can be coupled with the fact that when it comes to how on earth do you balance that resourcing, engineers are woefully underpaid in the UK, even compared to our European counterparts, let alone compared to some of the US markets. And so we're almost playing some kind of arbitrage with basically space salaries and semiconductor salaries with respect to operating in the UK, which always allows our money to go so much further than it otherwise would do if we were based elsewhere.
Yeah. Arriving at that prima payload or payload prima philosophy, was that immediate? Was that always the priority, or was that something you arrived at by trial and error?
I wouldn't say trial and error, but it was a development process.
Mm-hmm.
So we have always seen ourselves as straddling two horses, both the reentry architecture and the semiconductor architecture. Broadly speaking, they have to advance roughly at the same pace, because if you have one without the other, then the whole cycle can't close.
Mm-hmm.
The challenge, or let's say the challenge, more what we realized within these iterations of the development cycle, was that each point, actually, it was the semiconductor process was then driving the reentry architecture that was required, not the reentry architecture could drive the payload.
Okay, that's interesting. So your reentry strategy, if you will, and the designs for reentry were kind of guided by the material development, not the other way around.
Absolutely. So it comes back to this whole thing around you have to serve the payload. Mm. So that has certain power considerations, gas handling requirements, mass, and so forth. So there's no point in developing a reentry architecture that can't serve whatever it is that you're trying to produce, whatever it is that you're trying to return home. So it was a natural emergence through our development cycles that as the payload developed, we then had to look again at the reentry architecture as to best be able to handle what it was we were developing from an in-space manufacturing standpoint.
Yep. These, if you don't mind me asking, these kind of micro factories you've got inside of these satellites, are they, how sophisticated are they? You mentioned about the growing of the crystals early on in order for, in development of the substrates. Are they almost like little greenhouse factories for the development of the crystal, or are they more sophisticated than that, involving lots of different moving parts and so on?
So this is where, if you don't have an appreciation for how semiconductors are produced, you think they're really sophisticated. So people think of miniature factories. We've had a few people even ask us, well, how do we get an astronaut up there inside of that kind of space? Absolutely not the case. The best way to think about it is it's basically a chemistry set. And it's not a particularly sophisticated chemistry set when it comes to the process that you're undertaking. What is sophisticated is being able to basically ruggedize all of that technology to make it appropriate such that it can survive operating in the space environment. But as you touched upon, the actual process it's a growth process. So you're doing chemistry, you're mixing the molecules together, and you're basically heating it up to let a chemical process take place.
Yes.
And once you've finished with that reactor process, you have the finished product that you need, and then you begin on your reentry journey. So what being in space does is it basically provides us with an enormous running head start for the industrial processes we're looking to undertake, compared to if you were trying to undertake them here on Earth.
And what are the competitive advantages of the material that you can achieve by developing it in microgravity versus here on Earth?
So primarily, it comes down to the crystal structure. The crystal structure, you want the highest purity crystal you can achieve. And when I'm talking about the purity of that crystal, I'm talking about it from two different perspectives. The first one of those is that you need the crystal to be as uniform as possible. So an excellent example of this is like diamond compared to, I don't know, like other forms of carbon. Let's go for coal or something like that. One has 3 bonds and is black and awful and all sorts of other things, but it's a useful fuel source. The other one has 4 bonds, and due to some very clever marketing back in the 1920s, it's now perceived to be of great and rare value. And it's down to the purity of that structure and how well that bonding has taken place. So on Earth, you can create those bond structures in all sorts of crystals reliably and repeatedly. The challenge is that when it comes to something like a compound semiconductor, that growth process is very slow. And so what happens is gravity starts to have a profound effect on that growth process, that it basically just rotates one of the bond structures. And as it rotates one of the bonds, you have like a tiny little canyon appear. And you can see this under like an electron microscope. And then as one of those canyons appear, more of the crystals, the bonds start to rotate, and more of the canyons start to appear. So what happens is that basically the further away you get from the initial position of growth, the worse the crystal becomes. In part, microgravity prevents that from taking place, because it basically reduces a probabilistic outcome that one of those rotations can occur by virtue of the fact you have a much lower gravity environment. The second perspective as to why this is important is where things that aren't the crystal you're looking to grow start appearing. So on Earth, in semiconductor fabs and foundries and so forth, we create as high a vacuum environment as we can to ensure that basically this crystal can't be contaminated by other molecules. So you might be worried about oxygen, you might be worried about nitrogen, you'll just effectively be worried about the air that we're breathing could potentially contaminate something that is been undertaken in that semiconductor process. In space, you have pretty much the same sort of pumping speed with respect to keeping that vacuum maintained as you do on Earth. The difference between the two vacuums is the distance between the presence of molecules which could contaminate that process. So, for example, you're worried about nitrogen interfering with whatever process it is you're undertaking in a semiconductor fab on the ground. You can get that presence of nitrogen down to 10 to the minus 11. In space, at above 500 kilometers altitude, you would find nitrogen at 10 to the minus 22. So you go from being sort of, meters apart, tens of meters apart, to kilometers, hundreds of kilometers, even potentially thousands of kilometers apart from the next time that you would potentially hit a nitrogen molecule. Those two things give you a purer base from which to undertake the rest of the semiconductor manufacturing process, all of which is done once we return on the ground. The only keystone piece that is worth undertaking in space is that of the initial crystal formation.
I get it. I totally get that. I get that. What are and so then I'm guessing it's about getting the costs down of the launch and obviously the microfactory setup. It doesn't sound, from the sound of it, like there's a great deal of expense going into that beyond the spacecraft itself, but you don't have a lot of moving parts in there to actually develop the crystal. But then is it all about the economics of the launch and return?
Not necessarily. So
Okay.
it used to be. So when we started back in 2018, average price per kilo for launch, it's about $35,000, $38,000 a kilogram. It's now about maybe $5,000 a kilogram. So
Wow.
the collapse.
Okay, so that has come down a lot.
Yeah. In fact, it's actually ticking up the other way because there are so few people currently able to provide launch. But all of that aside, there's obviously been a significant reduction in the price per kilogram. It's if you get down to $500 a kilogram, which is what Starship is proposing to do under SpaceX, then humans could very realistically start paying to launch themselves. The aspect which now needs the most work is actually energy pricing. So space is currently our most expensive part, as you would expect. There's a whole bunch of engineering, there's a whole bunch of development, regulation, and so forth to get through. Plus it's albeit it has come down in price, it's still pretty punchy to get something into space and to get something back. But what happens is once you've completed that first return with that high purity grade crystal, my next challenge is the expense of running the terrestrial reactors that can take that crystal and continue growing it.
Okay. All right. So it's not complete when it returns. You've got to go and continue its development here on Earth.
So it is complete if we want it to be complete, is the way that I would...
It depends on the application it's going into.
Depends on the application. Yeah. So what we do is basically like what we bring back from space we call mother. So it's a bit like making a sourdough starter. We make the starter in space. On the ground, you put it into, crudely, another oven, you add more ingredients, and you bake it into a loaf, still of supreme quality. You then take some slices from that, and then some of those go on to become the next mother, while the others go on into very high-grade infrastructure applications. So the balance we're trying to now strike as Space Forge is how many generations do we want to produce against the kind of emerging cost base of keeping a semiconductor company running, and against basically the viability of supply. What you don't want to do is commoditize your supply too early, but you also don't want to leave it too restrictive that prevents you from entering certain markets. So we're trying to work out how many times do we go around this sourdough loop terrestrially to be the sweet spot.
Yeah, that's fascinating. And I think the analogy is wonderful with the sourdough. That's very relatable. It sounds simpler than I thought it would be, I guess, before our conversation today. But there's still a number of different, I'm guessing there are still a lot of different novel processes and technologies that you've had to develop in order to realize this. How much have you been able to port from other platforms or other industries, existing stuff, to kind of decrease the development time and increase your and accelerate the overall development of the business?
We've been able to port a huge deal, but all of the development and a core piece of our IP has been in being able to bring that technology across and then prepare it for space. It's in the preparation activities you have to undertake to qualify something ready for a launch. and ready for reentry, which is the big undertaking, what we do at Space Forge. It's still the same chemical process that we undertake on the ground to produce these semiconductors. It's just the virtue of the environment in which we're operating in that enables that. I would actually argue that the real novelty for what we do has actually come from the regulation aspects. So that's the thing that keeps me up at night the most. So to provide you with a very live example, we designed and developed the platform here in the UK. We then don't have much in the way of launch operators currently active in Europe. So we have to send it to America for launch. It gets launched from America and it goes into effectively international waters because you are in space, and space right now is basically treated like the sea. You then have the challenge that we are basically one of the only things that comes back from space more valuable than when it left. So we break all of the insurance models for space insurers because they're used to something that diminishes in value over time. We then, due to the regulatory environment, cannot return straight to the UK because we have to demonstrate our technology elsewhere before they allow us to land in congested at sea space as the UK, which is completely fair enough. But that means I land to Portugal, where we have an office in the Azores. So I land in the Atlantic. I then have the challenge that I didn't manufacture my product in Portugal, nor did I technically manufacture it in America, nor did I technically manufacture it in the UK. So at any stage where I land, I could be potentially charged import and customs for having landed there in the first place.
Wow. Okay. Wow.
So I have to figure out how can I basically use the Freeport network to get my product around into the different territories and the different customers I have. Or I run a hub and spoke model and I land it in the jurisdiction of the customers I'm serving.
And how cooperative are various customs officials being with you on this?
It's been a mixed bag. Some are very happy to help me. Others, the response was, what was it? There was one chap and he just went, I don't get paid enough to figure this out.
I'm sure. Wow. That is something. But you referred to that as the novelty, actually,
Yeah.
and that there are a lot of novel processes involved anyway. But you've cut and pasted a lot from various other industries, and then you've spacified them, if you will,
Yep.
to serve your needs. Where do you see? At the top of this show, we started talking about value and the value that's created along the journey. Do you see the value for you guys all consisting in delivery of the end goal? And what does that end goal look like, by the way? Or is there still a great deal of value that you can create in pursuit of that goal?
So there is already an enormous amount of value. So as a company, we already produce semiconductor substrates. We are already shipping those to customers terrestrially. The value in that is that we're one of the few providers able to contribute to a sovereign and resilient supply chain across Europe. So there are so few players that do the stage of production that we do. We're able to interface with a huge amount of supply chains in some really critical applications. So, like telecommunications, like building out more resilience for automotive, like data centers and so forth, amongst all the other, very obvious defense and aerospace applications that these sorts of technologies have. I would then say the utility for having platforms capable of re-entering back to Earth has not been lost on a whole host of other users, whether or not they are other in-space manufacturing companies, whether or not they are researchers in other verticals, whether or not they are the space agencies themselves that would have use for such a technology, and so forth. So we have seen all of those emerge. What I would say, though, when it comes to the end value point, is that I don't really think we have one. So I've always stated that I have a goal that right now, when you open up your laptop or whatever and it says Intel inside, I want to see it one day say Space Forge inside. The end point for me is that if what I do becomes boring, then I have succeeded. If making semiconductors in space is considered par for the course, then we have succeeded. If somebody switches on their kettle, they don't even realize that there is a chip somewhere in the grid that was produced in space, and that's the reason why it costs them less to have a cup of tea these days, then I've succeeded. Until that point is realized, then I won't ever consider us having achieved the full end value of what we do. Very crudely before, I have described this as I want to build Apple, but from space. But I actually think that does a disservice to how ubiquitous and abundant we want this technology to be one day.
Would you extend beyond semiconductors or semiconductor substrates?
In short, no. So we will facilitate other people to use our platform for other technologies. If they want to do pharmaceuticals, alloys, whatever it is, I'm more than happy to become a partner for them. But to me, semiconductors are the most critical technology of this century and likely the next century as well. In the 19th century, it was coal. In the 20th century, it was oil. It has become abundantly clear as early as we are into the 21st century how much of it is going to rely on semiconductors and microelectronics. So I don't think there is a more important technology that we were working on, especially coupled with space. And the next challenge of this is that there's basically no limitation to semiconductor materials that we could explore. So the technology approach, basically the chemistry set that we send up into space, could work across 14 different material classes, of which broadly about 5 or 6 of those are semiconductors. But within that, you then have basically an infinite combination of different semiconductor possibilities, some of which are already here on the ground and we're already using, again, gallium nitride, silicon carbide, and others that we basically theorize would make an excellent compound semiconductor, but due to the constraints of Earth, haven't been able to produce it in any meaningful quantity. And that's where, again, the next stage of Space Forge comes in. And the reason why I hold this view is that many people who operate in the subsector that is in space manufacturing will say, yes, of course, they're going to move into different materials. Well, each type of different material requires basically a whole other company and a whole other batch of expertise. Making a drug is very different to making a semiconductor. Making a semiconductor is very different to making a glass fiber optic. If you look at the way that manufacturing works on Earth, in like 2 cases globally, there happens to be a company that makes drugs and happens to make a semiconductor. And that's broadly due to some like M&A activity that occurred like 50, 60 years ago, not for any real strategic reason. And so I think it is much better to be focused on one particular area or one particular use case and work to best serving that customer. So as an example, if we are just producing our semiconductors and we return them and we stack them up and we just wait for an order, that is a terrible way to run a semiconductor business. You need 2 things. One, you need your capacity orders from one side so that you know where your orders are going once you produce the crystal. The second time is you have to deliver that crystal when your customer needs it. Because so much of the microelectronics industry and the industries that sit above that, automotive, telco, whatever, depend on just-in-time manufacturing principles. So at no point does anybody want to be sat on a huge pile of stock that they aren't able to shift. And so we have to work to those principles in order to do it. So eventually the way that I'd like to see it is basically we have Amazon warehouse-esque places globally where our satellites land and get delivered, and then it just goes out from there, and within 24 hours is with the customer type thing, because that's the way that the business model works, because that's the way manufacturing already works. Nobody who currently manufactures a product here on Earth will change the way they operate to include something from space. You have to take the thing that comes from space and make it fit the way in which we currently do things to have it adopted.
It is it's a very clear and inspiring ambition. I can, but tell me, it also sounds very expensive, and investors have pressures. So, do you have a sense of how much it's going to cost to deliver on this? And are there compromises along that journey for you? And if so, where?
So I would probably link back to some of the earlier things that I said, that you do get a level of cost effectiveness in the UK that you don't get elsewhere. The total capital requirements for something like we do is far less compared to other ambitions within both the semiconductor ecosystem and the space ecosystem. Average cost of developing a rocket is about $500 million. Don't need anything like that. Average cost of building a brand new fab is like 20 billion. Don't need anything at all like that. And that's, again, down to the virtue of the environment that we operate in. Because we go to space, there's a whole bunch of fab and foundry architecture that we don't need. Because we just need to get to space and we need to get to a fairly nominal orbit, we don't need anything particularly exotic about the launch opportunity. We can take the ride shares and basically the buses as they come along. The areas in which we focus as Space Forge are around, of course, the tool development and the reentry development. Again, everything else that we already do or leverage already exists. So when it comes to the investment appetite, I would say, and I'm conscious I'm speaking on my investors' behalf here, they have been pleased with how prudent we've been in not trying to do things just for the sake of doing them because we could. At the same time, while maximizing putting in the investors' cash into the two areas which yield not only the most value, but also the most benefit, and basically also the most ancillary benefits, that even if we should not succeed, we have basically made the world a better place for having attempted it.
Yeah. Yeah. It's, I find the economics on this surprising, but I totally hear what you're saying. Because if you're piggybacking, you're not building rockets, you're not driving launches, you're piggybacking on SpaceX and you're utilizing existing infrastructure. And you're focusing on the tooling, as you say, and on the other elements that you've outlined. And so I can see how that is far more cost efficient, I guess, to develop this than it would be on Earth. I think when most people think about semiconductors and space, immediately they're thinking in the billions, not the millions. But the economics have changed because of how far things have developed.
Yeah.
And also because I suppose, to an extent, the stage that you're working on, which is that very early stage and the supplying of that substrate. Obviously, for a variety of applications, and there will be tweaks involved, but you are providing the starting material if you want. It's back to the bread, the sourdough analogy. You're providing the starter, and
exactly.
So that is not the same as obviously running a fab or anything remotely close to that.
Yes.
Let's talk a little bit about how you're importing the skills, talent, and experience you need in order to build something like this out, because it is fairly innovative. It certainly sounds very innovative. I'd love to get your recruitment philosophy on this. Are you looking at really bright, high potential, lots of energy engineers and science and material scientists who haven't necessarily done anything like this before or done much like this before, but have their room for growth? A lot of startups go down that line. Are you looking to complement them with more experienced hires, people who've been around and understand different platforms and different technologies and materials and so on? Are you going for just the latter? How does it work for you guys? How do you see that kind of, the execution of your agenda with talent and the requirements you need?
Oh, so it's a blend of the two.
Yep.
When we started Space Forge, I was 26. And I consider my naivety at that age, when I thought I was mature, to have been probably the superpower that propelled Space Forge for the first few years. I would say that we have only gotten as far as we have because we have always been so willing to listen to the advice of others that we've worked with. And so we do also have, a lot of people, really getting toward the end of their career, but such that they've joined SpaceForge so they can share as much of their knowledge as possible before they do retire. And the way in which I crystallize that most is that I'm now 33 and I don't really know any 33-year-olds running a multinational space and semiconductor business with a satellite in space. And so the experience of which I've been afforded into a condensed total 7-year, but really 5-year period has been more than some people employ in an entire 40-year career. And that is also borne out broadly in our recruitment process. So you touched on it yourself. There aren't really nobody's really done this before. And so I can't go onto the market and say, hello, do you have 10 years experience in making semiconductors in space? Because even we don't have that, and we basically started it. So you have to look elsewhere for the experience, but you also have to look for the drive that makes somebody want to work on something as audacious as this. So I always know that it's probably not going to be a fit when I'm in the interview process and somebody asks me about job security. And I'm like, look, I could never promise anybody job security, but I could also never promise somebody job security in the way that I would argue if you're a FTSE 100 engineering firm or something like that. You also should not be promising people the job security because you simply don't know what's going to happen. So the only thing which I promise the team member when they join is that they won't ever be bored. And even when we've had people, who've been with us 4 or 5 years, grown up, matured, put a satellite in space and moved on, the one thing they say to me is like, Josh, you were right, I was never bored. And the opportunity that comes with that is we've become a rising tide that's lifted all boats, because when people have left, the one thing that they can say is about the experience that they gained. We've had our apprentice was hands-on with our satellite. Some of our interns last summer were hands-on with our satellite. Very few people on an internship are able to come back off of it and say, oh yeah, by the way, I've got to work on something that's now in space. So there are all of these philosophies which have emerged through this process that, broadly speaking, we hire for passion and we hire for drive. And I know that there are endless amounts of companies that will also say that they do the same thing. I think the thing that sets us apart in SpaceForge is not seeing age as a discriminating factor when it comes to either recognizing that drive and passion or recognizing that experience. I think I saw a quote somewhere, it's probably on LinkedIn or something like that, but it said, do you actually have 10 years experience, or do you have 10 years of experience doing the same thing every year for 10 years? Like, did you actually grow?
1 year of experience 10 times. Yeah.
Exactly. And the way in which I think that is best crystallized is the Apollo program itself. So the average working age of an engineer on Apollo, I think Apollo 11, it might be in the entire program, was 26. The same age when we started SpaceForge. And roughly, I am the average age in the company at any given moment, because of the amount of people that joined us early on and have grown up with us, equally where we've hired an abundance of long-term excellent experience at the other side. Broadly, I've tracked that. Now, I think if you look at the space industry in general in the UK, I think the average working age in it is like 58. I can't remember what it is for the semiconductor industry, but I know it's not far off. Both of them have these perceived enormous skill crunches. So the challenge is it's not for a lack of people studying engineering. It's not for a lack of people studying chemistry. It's knowing that the roles exist in the first place. Like, semiconductors are cool. Space is cool. They are not hard propositions to sell and make sound interesting, because you're working on such fundamental technologies that underpin pretty much everything we do.
Yeah.
So I appreciate that was a really long view into my recruitment philosophy.
Don't apologize. I was talking to founder CEO the other day, and he said that when it comes to hiring, they too have the policy for the most part. And they've been around since around the same time, 2017, 18. And he said he finds hiring the toughest part of his job. He said, because I'm making the decision largely based on the way I feel when I'm around them. Do they excite me? Do I come away from that engagement feeling like they could do it? He said, I understand the structured questions to ask and these different assessments and so on, but I can't get behind them. The only thing I can kind of get behind to determine whether they're going to be a fit is how excited I am to work with them. And he said, and I appreciate that's probably not something you're going to find in the golden rules of hiring, but that's how I've operated. And so far we've gotten to the point, and they're a very well-known deep tech company in Europe, and they've had a lot of, they've accomplished a lot of milestones. They're doing well. They've raised a lot of money and all of this. So it's clearly worked. It's clearly worked to an extent. Do you see it in a similar way, or the
Yes.
hiring process, and in particular that kind of assessment of this thing called potential or energy or drive and motivation, and recognizing that that people are different and they have different ways of communicating these energies, these features, if you will. But do you see that in a kind of similar way?
So I'm not an engineer by background. And I have found that one of the hardest parts of my job has been getting an engineer to trust their instincts. And that is true for hiring as much as it is any other aspect of their job. It's something I rely on a lot when it comes to this hiring process, when it comes to trying to navigate the regulation, the politics of what we do, the customer engagements. And I appreciate that comes to me more easily than it does others in my team. But
what comes to you more easily? The intuition?
I wouldn't call it intuition. I would just call it my gut. But I think that's also a demonstration of the different skill sets required in industries like these. The perception is often that unless I'm an engineer, there is not a role for me within semiconductors, within space. There is an abundance of jobs out there for people who don't come from these sectors or don't have the technical background to fill, because there are. The way I would put it is that I once heard the joke in the space industry that only 10% of us are ever allowed out to play. And it's true. I work with some incredible people, but they would run a mile if I asked them to sit in front of a government or sit in front of a camera to talk about what it is that we do. And if they were willing to do it, they would talk about it in such an astonishingly deep knowledge of how proud they are of the technology that the audience would be lost. So one of the things I bring is trusting my gut when it comes to making some of these decisions.
Mm. Mm. And to make those decisions, to trust it, I suppose you've got to, sorry, I'm just kind of riffing here a little bit, but I suppose you've got to believe 100% in what you're doing. You've got to be 150% focused as well. You have to know kind of exactly where things are at and what's at play. And, it's got to completely consume you. And you've got to, and then I think when you're evaluating talent from that perspective, and you're then operating from your gut. And gut and intuition, for me, feel like the same thing. Maybe they're not quite, but for me, they feel more or less, it's that voice, it's that urge. It's almost like an urge. It's a compulsion. I have to do this. I have to do this. Or I have to work with her, or I have to hire him, whatever. But the intent, but there's something, I wonder if there's a relationship between that intention, that I'm so committed to this, I'm so committed to seeing this right, and then making that decision then too, in order to have a chance clearly of getting it right. Does that make any sense?
Does. I think the way I would describe it is, I've been building Space Forge longer than I've ever worked anywhere else. So it's got to the stage now where I just don't know anything else. In many ways, I've got so much experience, I would probably never have to worry about getting a job ever again. In many other ways, I'm so deeply unemployable for having been able to create and build something for so long that I've got no doubt that I would really struggle to fit back into a corporate. And that comes with its own set of responsibilities, its own set of challenges, but also its own type of fun. And it's less even about the drive and the passion. Every startup has bad times, and that's where the companies are really forged. But it's also like, are you actually having fun? Are you actually enjoying it? You like, most of all, you have to enjoy what you're working on. Because I've worked with many people in many other jobs where they were not enjoying it, and they were bloody miserable. And the single best piece of advice I was ever given was never choose a job based on its pension, because you don't know if you're going to see it. And it was one of those pieces of advice that made me start Space Forge in the first place. Because I was like, again, I have to do something that matters. I have to do something I'm actually going to enjoy. And I have to do something that, for having tried it, ideally the world would be better, at least in the attempt, if not the success. And so if you're not enjoying it, then don't do it. Go find something else. Yeah. There's more to all of this than just getting through doggedly the bad bits.
Absolutely. And that's where startups excel. And in fact, that's probably where they're completely unparalleled. Because the multidisciplinary nature of what you're learning and how you're learning, it's hitting you on every single level. Yep. It never stops. And you feel that, and it's yours, or it's partly yours, and it's everyone else's. And so it bonds that team together in a common mission. And, especially in deep tech, you're naturally doing something audacious. You're going for, you can be inspired by the goal. You're not making accounting software. No disrespect to the accountants or to accounting software, but you're doing something that clearly is going to impact things one way or the other. Josh, thank you so much for joining me today. This has been marvelous. I have thoroughly enjoyed our discussion. I've learned a lot, and you've, I think, what you guys are doing at Space Forge is hugely attractive, and we will watch with interest.
Excellent. Thank you so much for having me.
You've been listening to the Lab to Market Leadership Podcast, brought to you by Deep Tech Leaders. This podcast has been produced by Bauhaus. You can find out more about us on LinkedIn, Spotify, Apple, or wherever you get your podcasts.